Hello and welcome to this next lecture on machine learning. In today's session, we will continue our discussion with logistic regression. As already described, logistic regression is a foundational block for neural networks. So recall that we began with a simple perceptron, and to make it differentiable, we introduce a sigmoidal perceptron where you replace the step function with a continuous approximation which has this particular form 1 by 1 plus e raised to minus s. Of course, in this process we also decided to rescale to the interval 0 to 1. So what we have done is applied sigmoidal function to the linear combination of the features, which is W transpose phi x. So phi is a basis function representation. So we also provided a probabilistic interpretation. The probability of class 1, probability y is 1 given x, can be interpreted as this sigmoidal form applied to the linear combination of features. You can also get the probability of class being 0 as 1 minus this function. For today's class, and in fact for some of the subsequent discussions, we will refer to this probability of class 1 as fwx. Think of this as a regression function, but it has an interpretation with respect to classification. Probability of class 0 is 1 minus fwx. So the estimator w hat needs to be found. Now, like before, we can find that w hat and estimate w hat which maximizes the likelihood. The likelihood is viewed as a function of the parameters given the data, and we want to find the parameters that maximize the likelihood of the data. So w hat is max over w of likelihood of the parameters given the data. In this specific case, the occurrence of any class label is basically a Bernoulli event. So y is 0 or 1, and this basically forms a Bernoulli event where the probability of class 1 is nothing but fwx. So as before, we look at the likelihood as the product over all examples which are assumed to be independent and analytically distributed of the probability of seeing a head, that is fwx, and this is instantiated if you actually find a head, that is 1, into 1 minus the probability of tails, and this gets instantiated if you actually find a tail. So substituting for these values, we get the expression shown above. So this overall is the likelihood. So if yi is 1, then the second term becomes a 1, basically anything raised to 0 is 1, and the first term surfaces, else it is second probability of class 0 that becomes prominent, and the first term just becomes 1. So this is the maximum likelihood estimator for w, viewed as a function of the data. Well, if the data is random, then it's an estimator, it's a function. For a specific instance of the data, you call it estimate. Specifically, this is an estimate. Now one can make transformations to the objective and look at equivalent formulations yielding the same result, the same maximum likelihood estimate. So for example, one can look at minimizing the negative log likelihood, that is EW is minus 1 by m log of probability of D comma W. Now you can derive the expression for EW and you realize that this is actually a cross entropy loss function. So likelihood was gain that had to be maximized. Obviously you need to minimize the negative of that, but you are not just looking at negative, you are looking at negative of a monotonic transformation. So this cross entropy loss function is negative of monotonic increasing transformation of likelihood. So what does it look like? Well, as I already said, you are interested in W hat, which is now arg min over W of the negative of the log of the product over all examples of the probability of class 1 raised to yi, probability of class 0 raised to 1 minus yi, and this is again the same as follows. So you basically now realize that the log of a product is the sum of logs. So arg min of minus of summation I equals 1 to m of the log of the remaining terms, but the log of these two terms, the log of the product of these two terms is again the sum of the logs. The exponents, the log of a raised to x is x times log of a. So this can be basically simplified as yi times log of fw xi plus 1 minus yi times 1 minus log of 1 minus fw xi. So let us substitute for fw. So recall that fw is 1 upon 1 plus e raised to minus w transpose phi xi, and 1 minus fw xi is e raised to minus w transpose phi xi divided by 1 plus e raised to minus w transpose phi xi. So with the substitution you get this form, and as I said you can expand this fw. So let us do that. So you can substitute for fw as 1 upon 1 plus e raised to minus w transpose phi of xi e raised to minus w transpose phi x I have the same denominator 1 plus e raised to minus w transpose phi xi. What you can do thereafter is as follows. So the log of ratio is the difference of the two logs. So this basically will become log of 1, which is 0, 0 minus log of 1 plus e raised to minus w transpose phi xi. The second term, the log basically will be log of e w transpose phi xi, which is basically minus W transpose phi xi minus log of 1 plus e raised to minus W transpose phi xi. Now one can actually write this slightly differently, and I am going to do that. Instead of this representation, I am going to represent 1 minus Fwxi as follows. So the numerator, which is e raised to minus W transpose phi xi, can actually be divided from both the numerator and denominator. So that way you will get the following numerator will become 1 and the denominator will become as follows. You will get e raised to W transpose phi xi plus 1. So note that you have actually gotten rid of the minus sign. So this is the denominator. One can multiply the numerator and denominator by e raised to W transpose phi xi, and I will do precisely that to get slightly different representation. So we will get e raised to W transpose phi xi divided by e raised to W transpose phi xi plus 1 will let us express the logarithmic term slightly differently. So now I can represent the log as follows, is W transpose phi xi minus of log of e raised to W transpose phi xi plus 1. Likewise the second term will just become log of 1, which is 0, minus log of e raised to W transpose phi xi plus 1. So these will be our final expressions. Now with yi times the left hand side plus 1 minus yi times the right hand side, what you notice is the yi times this term log of e raised to W transpose phi xi and minus yi times this second term, that component gets cancelled out. What remains of course is minus of log of the e raised to W transpose phi xi. So that is what we see here. We see yi times W transpose phi xi and 1 into minus of log of e raised to W transpose phi xi plus 1. So you can rearrange terms in different ways, and one rearrangement gives you this expression. What is this expression? So recall that the sum of unsigned distances of the misclassified points from the hyperplane for the perceptron was precisely this, is a unsigned distance from hyperplane for perceptron. Of course now our yi's are between 0 and 1, so semantics have slightly changed, and we also have this minus of log expression. So basically this is the modification incurred because of the probabilistic interpretation. Now you have the summation over every data point irrespective of its misclassification, and this basically means that every point contributes, and basically the error is minimized when the signal of the misclassified points mixes well with the wrong signal generated by the model classifier. Now this has an interpretation in terms of something called cross entropy. So you could think of the log terms here as encapsulating the bits needed to identify an event, an example x. This is based on the model distribution. So average number of bits needed to identify an example x drawn from a data set D. Now the thing is, the average is computed on the data set, whereas the bits compression coding scheme is using the model probability distribution. So coding scheme that is used is optimized for a model probability distribution. On the other hand, the average is computed with respect to the data set, that is the yi part, or the 1 minus yi. The log part here is basically the model probability distribution. So the expectation is computed with respect to the data set D, the empirical distribution, whereas the compression scheme is with respect to the model distribution. Now one can do gradient descent for logistic regression because there is no closed solution to this cross entropy loss. So if you apply the gradient descent with wk plus 1 is wk minus eta times the gradient function. What is exactly this gradient? Well, one can first of all take the gradient of this entire entropy and realize the yi's, the expectation basically, which is a sum, and you can basically write the gradient as a sum of gradients. So this will be the sum of these gradients, and that will be gradient of log of fwxi weighed by yi plus 1 minus yi times gradient of log of 1 minus fwxi. Again, one can substitute for fwxi. So recall that fwxi is 1 upon 1 plus e raised to minus w transpose phi xi. So one can apply chain rule and realize that this gradient is nothing but phi xi times a factor. What is this factor? Well, this factor is nothing but the probability of y equals 0 given xi. Similarly, one can compute gradient of log of 1 minus fwxi. So after some simplification and substitution, one gets the final descent update as follows. So when you substitute for the gradient of log of fwxi here and the gradient of log of 1 minus fwxi here, the second term, we find that some of the terms involving the exponentiated factors, they get basically cancelled out. So you are left with a very simple form, the summation over all the data points, the difference between the true output and the predicted output, the probabilistic predicted output, the difference between true and predicted probabilistic output multiplied with phi xi. So basically the update is a linear combination of the phi xi's, but the phi xi's contribute in proportion to how much the prediction for that point differs from what it is supposed to be. So this is the iterative update rule with every point contributing. A stochastic version of the same is when you are looking at any one misclassified point. And what is a misclassified point? We mean that fwk xi is greater than 0.5 whereas yi is less than 1. Which means y is 0, or fwk xi is less than 0.5 and yi equals 1. how do you contrast the update above with the earlier step function or perceptron update? So recall that for perceptron you looked at any misclassified point, and misclassified point is where there is a sign mismatch, and you update proportional to the feature vector for that point scaled by yi. On the other hand, here you are basically looking at a misclassified point but scaling not by yi but the difference between yi and the predicted value. The difference is only because earlier the predicted value was either 0 or 1, here you have a continuous prediction, the probabilistic interpretation to the prediction. In fact, this update for logistic regression is very similar to that for linear regression which we have seen earlier. So it turns out that there is a whole class of models called generalized linear models for which the update rules are very similar to that for linear regression, or as we saw now, logistic regression. That is because linear regression and logistic regression are just special cases of generalized linear models, and the basic characteristic of generalized linear models is to apply a function g to W transpose phi x where the function g is fixed. Recall that we also discussed non-parametric regression where the function g was not really fixed. One can also regularize logistic regression by having a penalty for weights. This is to discourage extremely large values of weights, and like before, the motivations to avoid overfitting. All we have done is added this penalty function to the original cross entropy loss function. Now, is there a probabilistic justification to this? It turns out that the W hat that you obtain by minimizing the cross entropy loss and to that you adding 1/2 lambda by m W square is the same as W hat, which is the maximum a posteriori estimate for logistic regression, which is nothing but the W hat that maximizes the posterior of W given the data, but this is assuming a prior on W, and the prior is again to discourage extremely large values of Wj, and that amounts to the following. So assuming that W before you saw anything followed a normal distribution with mean 0 and covariance matrix 1 by lambda I. So recall that this basically meant each Wi was univariate Gaussian with mean 0 and variance 1 by lambda. So we will reinvoke Bayesian parameter estimation a little systematically to show this equivalence. So the regularizer is all because of Bayesian inference applied to logistic regression. So the prior as we have already motivated is assuming multivariate normal distribution for W, and we basically make use of the 3 sigma rule, which basically says that each Wi is approximately upper bounded by 3 divided by square root lambda. So most 99% of the Wi's will lie in this interval. Lambda is basically the precision. If we know W very precisely a priori, we will start with a very high value of lambda. So this is a specific form for the prior of W. Now the map can be obtained as W hat that maximizes the product of the prior, which we already seen, and that of the likelihood. which is something we already seen through MLE. Now what does this amount to? Well, this basically amounts to the following. Like before, we can take some transformations. This is nothing but argmin over W of minus of log of the prior minus of log of the likelihood, and we know that the minus of log of likelihood can be simplified to cross entropy loss, whereas we have enough intuition to understand what this prior will mean. It will basically mean minus lambda by 2 norm W square minus of or plus of log of 2 pi by lambda is to m by 2. Now the second term will basically not contribute because we are looking at argmin over W, which this term is not a function of. So the other two terms will remain. So basically we have substituted, and with some more simplification we get to this form min of the regularized logistic cross entropy loss function. Thus map can be found by minimizing the regularized cross entropy error. So this regularized or map estimate for W is supposed to be more robust against problems such as overfitting, and therefore preferred. One can similarly apply gradient descent to regularized LR the way we have applied for the cross entropy minimizing LR, and the descent update will just have an additional adjustment term in the form of minus lambda times W. One can also adapt a stochastic version of the same. So you are trying to ensure that the new value is not too far away from the previous. One can also extend logistic regression to multiple classes. One way you can do that is have a different weight vector for each class. So WC is a weight vector for class C, which could be either of 1 or 2 or k minus 1. You can do that for all the k minus 1 classes, and to ensure that there is normalization, you get the probability of the kth class as 1 divided by 1 plus the same denominator, the numerator is 1. So this for k equals 2 we get what we already discussed. So probability of the second class is 1 upon the summation, and probability for the class 1, which we call class 0 so far, is e raised to minus W transpose phi x divided by this same denominator. There are other alternative extensions to multi-class logistic. For example, you could also have a different vector, weight vector for every class, and instead of this denominator which had a 1, now the denominator is simply the sum of the numerators across all the classes. One can show that these are equivalent. So as homework, prove the equivalence of the two formulations. Thank you.